Hey everyone, welcome back to Native GIS Today.
Hello everyone, welcome back to Native GIS. If you are new here, this channel is about GIS, Python, GeoAI, learning about ML, and new GIS related industry videos, how they have been integrated, all those things. So now here's the bigger plan. What we have decided in this channel is we'll be starting. We have already started it. We have already started the Python series in native GIS. How the GIS and Python projects can be built. We have already started creating some new projects on it. So you can check out the new video, the previous video which we have created. So similarly, this is also the second part of it, and this will be like a series of videos will be coming in this year. And yeah, stay tuned. You will be get to know what we are developing over here. So basically, to give you overview, I have started a Python GIS project since where we build small portfolio ready projects that you can finish quickly, but it will still looks as professionals. Okay. In this series, we'll be covering various projects like building footprints, which we are today we will be going to work on it, like flood risk maps. You can say EV charging demand, forecasting how it is, population density, NDVI, vegetation health monitoring, route optimization and network analysis related projects. Also some GeoAI related projects also, but which I was planning to create another series on that, and will be adding that to a playlist so that it will be helpful for you and you can work on that. And I'll clearly say you, like the goal is simple. Here I am also learning, and I'll try to make you learn what I am learning as well. And yes, we both can learn and grow our portfolio. So the main simple goal over here is you can build a portfolio of projects. You learn the real workflows, and you can teach others as well, right? So let me know like which city are you from, and write down in the comment section so that what kind of GIS are you working on, and what kind of GIS you want to do. Utilities, urban planning, environment, remote sensing, or you are already into the GeoAI and you are working on it. So basically, this is not the theory. This is the practicality and the portfolio GIS which we are building. Okay. Thank you. And now we'll be starting with our project, which will be today we'll be going to decide. So what we the topic that we have already decided is creating this building footprints from imagery. No ML, but yeah, we'll start from the basics and how we have done, and we'll create a whole portfolio, whole list of things like how we have done it. So this is basically will be a live session, and I'm recording it. I'll be putting it in YouTube. This might be a 2 hour session or 3 hour session, but I'll always put let's say a short video of it, and which I'll be putting it after I record it after 10 days. I put it in the in our channel. So if you want to view that, if you don't want to view this long hour sessions, because in the this live video I actually do it and show what are the errors and everything. So this is beneficial for those who will be working alongside with me. So that is beneficial for them. And if you want to just learn like what is this project about, and how I have done it, what is the analysis, what is the end product of it, you can view that video. It will be might be 20 to 30 minute video, and you can learn from that as well. Okay, and let's now go and start the video. Okay, so today I'm going to show you something powerful, like how to go from aerial imagery to building footprints using only Python, no AI model, no training, nothing, just classic computer vision to detect edges, clean shapes, and polygon, and then we'll be forming a GeoJSON file. Okay. Why is this beautiful, useful? Okay, so because in GIS you often need a fast baseline. Okay, maybe the building layer is missing. Maybe you are doing quick urban analysis, or you are building a portfolio and you want a real workflow, right? So the basically the just will be by the end of this live video you will have a building footprint GeoJSON, clean before after and after visual, and a quick comparison versus OpenStreetMap. Okay, so even without AI, you can still extract building footprints if you understand the pipeline. Okay, how you are going to do that. So now let's go to the project objective. Think of aerial imagery like a photograph taken from above. Okay. So buildings have roof boundaries. If you have observed, like there are roof boundaries which have been created at the top of the building. Those boundaries appear as a soft changes in color, meaning pixel change quickly. Okay, so we do this, make a image cleaner, boost the contrast of that image so that the roof stands out. Then we detect the edges, convert edges into the shapes, and export those shapes as polygon. Why this is required in basically in terms of GIS is because building footprints are used everywhere. Okay, like you can say that in urban planning, disaster mapping, expansion planning, telecom network, and like infrastructure asset planning. And sometimes the building layer is missing or outdated, or you need a basic baseline of your for your projects or for your work or something like that. Okay, so basically this will not be a perfect. Roads have edges, trees have shadows that can confuse it, but as a baseline pipeline it can be a great portfolio project. And this project teaches you the GIS skill of turning pixels into polygons. Okay, so basically, before what I told regarding why this project matters in and where this can be used in real world use cases. So, which I say that rapid mapping, right? Quick building, create quick building footprints for places with missing data, disaster response that can be like first build up footprint, estimation of exposure mapping, urban planning, let's say estimate build density, detect new construction areas with multi-rate imagery, and you can say like utility plus you can say telecom, understanding the building distribution, supports network planning and service rollouts which are there. So now who benefits from these projects? GIS analysts, planners, humanitarian mapping teams, utility, startup building maps at scale, and also you guys. Okay, you can build a portfolio. Now, what are the GIS and remote sensing concepts that are used? So, first is raster versus vector, area of interest clipping, CRS, units, pixel resolution limits, image pre-processing like grayscale, CLAHE, denoise, gamma, then Another will be edge detection, morphology, the raster to vector conversion, simplification, area filtering, lightweight validation, again OpenStreetMap buildings. Okay. Also, I have, as discussed previously, like what will be the final output of this. So it will be before versus after visuals, original imagery versus the enhanced ones, then the edges and candidate footprints, which are we will be developed. A candidate footprint layer of like the GeoJSON or a set file, you can say. Tiny evaluation table like overlap percentage, IOU of sample tiles which we have get, and 1 to 2 clean maps or static versus plus interactive value. So the clear goals which we have is I'll be also adding this to the GitHub, and where you can view that thing in that the whole project structure or the workflow, JS workflow that we have created. I'll be adding that particular architecture in that GitHub repository. So I'll be building that after this video, and I'll paste that in the description of this video as well as in the short video that of that 30 minute which I'll be create. There also I'll add it, so you can easily go and check out what I have done in this project, and you can also clone that thing and you can work on that. Okay, that's always a GitHub portfolio goals which you can build, and from that you can as well learn like how the project architecture has been built. So basically we'll be developing this in the Google Colab notebook. So we'll be starting with the into like what is the age based footprint and extraction, uh, how we'll be building it, and then the data sources that we are taking, mainly we can take NAIP imagery, that is via Microsoft Planetary, OSM buildings via OSM NX, and environment setup will be the installations of the libraries, imports, and quick checks. So that will be doing AI selection that will be doing based on the imagery or aerial imagery that will be picking up. Then how we'll be loading that imagery, pre-processing it like grayscale, HSV value, denoise, uh, contrasting it, or then gamma and shadow handling. How that can be done, we'll be explaining that as well. Then the edge extraction, how that will be done, like fine tuning it. Then multi-scale combination of doing that. Then post processing it like morphology, close or open, connected component size, filtering, edge density, then you can say that the other one will be the vectorization of it from like contours to polygon, simplification plus tiny fragment removals, and then export it to GeoJSON or set file. Then evaluation of this results that we got from this whole process, then mapping it, then we'll share the results and insights, and then we can share the what are the next steps that we can do. Okay, how we can build a AI tuning model, and then how we'll be functioning on that, and then those things will be discussed a little bit because we can set that to for you for our new GeoAI project series, and then we can discuss on that. Okay, this is not the AI part. This is only pure based Python thing, and how we'll be developing that. That is the whole thing which I'll be adding over here. Okay, and now let's go to the libraries that we'll be using, and we'll explain what are we are using and why we are using it. Okay, so basically for the GIS we are adding the NumPy, Rasterio, GeoPandas, safely pipe project. Okay, so NumPy is basically for maths, pixel maths, mask threshold, Rasterio is to read and write the geotapes, handle means georeferencing. GeoPandas we are using for to handle the polygons, to export geotation or the shape file which we will be doing. Then safely, it is basically for the geometry operations, simplify area and interactions, and PyProject for CRS transformation, degree or meters areas. Okay. So imagery access that we'll be doing will be PyStack client query stack catalogs, and we'll be getting it planetary computer sign planetary computer stack assets, and we'll get that from that. Image processing OpenCV Python, that will be CV2 for grayscale blur, contrasting Canny morphologies and contours and everything. OSM reference can be through OSMNX. That I guess you should be knowing that, and visualization matplotlib and folium. Okay, then we need to find a good AI for this project. Why we are why we need to get a good AI is, as also we are doing it in Google Colab and my system is not so good, so I'll not be taking a big larger scale area to perform it. I might be taking a simple and small area for checking that. And why we are doing for this good AOI is, basically the concept is age detection work best where buildings have clear roof boundaries and fewer trees. So we need to be picking a suburban block with gray streets and visible roofs. So there are some cities which I have figured it out, like let's say Arizona. There are these things are there. Okay, so like California, Colorado. So all those have a particular this type of detection where they will be working. But yes, here this is the limitation as well. Let's say in our country like India, the buildings are very close to each other, so age detection is very difficult. But yes, we have AI models which have already been developed for which can detect those edge boundaries and map it out, which we'll be discussing in our next or in the GeoAI project series, when we'll be discussing this building footprint part and how that has done. We'll explore that as well, like how using that model also we can do that. But yes, we should know the basics as well, and what are the limitations of this as well, right? So we'll be going through it, and we'll be seeing like how this can be done. And let's go into the coding part now. And all theory part has been covered. What we are doing, how we are doing, who will be benefited from this. All these things has been done. So now let's go and build this project side by side. You can also develop this project by checking what I'm doing. This might be a long session, but yes, it's already a 18-minute video. So if you are still there with me, then you are great and you are supporting me. And I guess I deserve one like for this. Please like the video as well. Okay, thank you. And let's now go to the code part. Okay. So all right, let's jump into the Google Colab. So for this project, Colab is perfect for this series, for this project, because it runs in browser. There is no heavy setup required. Anyone watching can copy the notebook and run it. And by the way, if you want the notebook and outputs, I'll put everything on the GitHub after this live session, and just comment footprints and I'll pin the link. Okay, and first we'll install GIS plus computer vision libraries. Uh, in Colab, we'll install once per session. So let's now go and install it. Okay, I'll be starting the code and I'll be writing it. So now let's write it. Install Rasterio. My focus my your lead. And then other one store CV Python, that is CV2, which we are writing. Okay, all this stack plan. I'll be adding this notebook file in the Google Colab. Okay, so you can check this out, or you can code by myself. I mean, code by when I am also writing it. Okay, stories. Okay, so basically, step one, when we'll be installing this Rasterio, this is for reading geo-referenced imagery like geotapes. It understands map coordinates. Okay, installing OpenCV. Basically, it is a computer vision engine. This is where Canny edges and morphology happen. Okay, GeoPandas. And safely are for polygons. So we can convert the image blocks into building footprint shapes. Okay. Then pipe project or pipe pros, which are with this I am written. So this is basically for helps with CRS transformations because degrees are not in meters. Okay, and Folium and Matplotlib, which are for creating the interactive maps, and PyStack client. Uh, this one, PyStack client planetary computer. This is are how we search and access any IP imagery through a catalog. Okay, so if you have different data source, you can use that. But what I'm showing for today will be from the NAIP imagery catalogs, and I'll be working on that. So OSMNX, OSMNX, yeah, that is for fetching the buildings for validation. Okay. OpenCV finds edges, GeoPandas turns them into GIS layers. Okay, great. Now we'll be importing the files. I think it has already done. Okay, let's now. So before it as well. So let's add a text file and what you are going to do, import everything in raster plus your visual flow. Okay, I have already written this, so that's why I'm writing it so that it will be helpful for you guys. Okay. So let's start with. So I'll be now importing our libraries, NumPy, then Rasterio, OpenCV, GeoPandas, Matplotlib, Folium, Stack, Planetary Computer, OSMNX. Okay, so we'll be importing them. I have already coded it, so actually I am sometimes checking the other code as well, that I am writing it correct or not. Okay. What I want is I want to give you the correct thing. Don't think like okay. Import null now can I post when planning import CLAHE. Okay. So I'll be writing it now and then I'll be explaining it what we are doing and how we'll be going into the other step. Okay. So this is also a benefit of Google Colab, that it will show you like what can do it, because if that is not necessary, so it can also show you. Okay. Like this, it was so done. So it can be done like that. So basically, we have either Rasterio and respective functions that we need to be from that library. In GeoPandas, then safely, Pythos, then CV2, OpenCV, Matplotlib, and Folium by client. and okay, run it. So basically, NumPy is for pixels and arrays, Rasterio is for pixel with map coordinates, OpenCV is for image processing, and GeoPandas and simply for the polygons, and matplotlib is for visualization, statblr that will be for image research and access, OSMNX that is for OpenStreetMap buildings. Okay, cool. Now we'll be defining our AOI. Okay, AOI is how GIS controls the scope. Smaller AOI, faster processing, and clear demo that we can provide it. Okay, so let's now define the AOI box and go. Okay. So I have already the values. So I have Gilbert, Arizona, some coordinates. Okay, so I'll be pasting that directly. And the AOI that we have is from the Gilbert, Arizona. Okay. Then what we are doing and why we are doing, I'll be writing. Okay. Why this means that box which we have provided, right? Why will we build out safely polygon for the AOI. Okay. But the result that can be added will be can pass this method to Horizon, where is it? So already it came. Okay. Why not? GeoPandas then so I think we need to passing this on option. CRS, that is simply 496. So okay. So this is basically why, because if we will try to process a whole city, our system will run. If we will processing for a small box of area, it will be fast, clear, and we can complete this tutorial with time. And so I am using this simple bounding box. Okay. Uh, yeah, simple bounding box. Like we'll be giving west, south, east, north, and after that, and I convert it to a polygon. Okay, this is the CRS coordinate was for latitude longitude. That's why I have provided EPSG4326, which is basically latitude and longitude. Uh, so basically, okay, I'm getting this. Why? This is there. Okay. So these small things also you need to take. Yeah. So I was explaining about the CRS part. So EOI coordinates are in degrees. Okay. but later we will calculate area or overlap only meters. So that's why CRS matters. So degrees are not meters. CRS is how GIS gives into the meters and everything. So that's why we have converted it. Got it? Yes. So this is let's run it. Okay, we get a polygon as a feature class. Means we get a polygon feature. Now we'll be download or load imagery that from that NAIP stack. Okay. Okay. Now we're downloading and in this thing. Okay. We'll make now let's start with what we are doing. To start with imagery. Okay. So what we'll be doing is so I have already the stack URL. Okay, let's see if it is working or not. See that. Okay, we have it. For this one. This one. Yes. Then we can get, let's see. Okay. Now, put it into a list. Use. Records map. Okay. This one. Okay, we got a error. What is the error? No attribute. Okay. Actually, my let's see. So basically, we are loading the imagery. Okay, this data set is in AIP, which is a high resolution aerial imagery for US, and we are using Stack catalog. Stack is basically a searchable library for geospatial datasets. So we search NAIP using our AOI polygon. We see that how much uh, from our data or the polygon that we have taken, it intersects with that particular catalog data available, and then it will be providing us the list of data available, and we'll say that the images that intersects this area, and we got a length of the items that we have. Okay, so now we can see that the items that we have is 7, means total 7 uh, total 7 images, or the imagery that we can found out that it is already there. Okay, now let's start with the other part. Then pick the most recent NAIP. Okay, now let's pick up the latest one, latest NAIP part. So pick up the most latest one, that will be okay. So for that, items. So usually there are multiple layers of data available for our demo, or for our this portfolio series. We pick the most recent one. Okay. Okay. Python will see like why it is giving. No, but I'm saying like why now it will be providing, I guess, the imagery item, basically the one imagery product for our AI. Okay, we got one that is of 2023. Okay, 23 to 24, I guess. Okay, 19/01 2024 and 15 now. So that is basically the image which it has provided us. Okay, 59 2023. Yeah. So now what we do is we read the NAIP. Okay, click to AI and to numpy array. Okay, so because we only create the pixels inside our AOI, so clipping saves time and makes our project quicker. So basically now we'll be reading the imagery. So planetary computer needs signing, so we'll sign the asset link. Then Rasterio will be opens the GOT if notice something important. Like the imagery has its own CRA, so we reproject our AOI. After that, we convert into the raster CRS before clipping, and then we need only one window inside that UI. Finally, we'll be converting that into our normal image array, save height, width, and channels. Okay, so that what we'll be going in this code part right now. So let's find it out. Okay. So maybe so like stores imagery. So I can suggest you one good thing. Hear some piano music while you are coding. It is very good. Like you will be focused and you will be working on that. Okay. Asset underscore So what we'll be getting is like, okay, okay, cloud optimized geotech. So let's see what will we got some error. Okay, here we go down. Okay. Start. Okay. So it will be like it will open function. Okay, that's all open. So basically, this will be providing us to get a small RGB array with a correct transform geo for georeferencing part. We'll be getting a proper array of things. Okay. Yes. Yes. Total bound is there or not? Yeah. Everyone know window equal to most transforms transform. You have it declared it above. Transform transform transform. Okay. It can directly take it. No worries. Then, ask. Okay. What we will be taking is the first three. Okay. Force 1, 2, 3. Then as a window provided here. Then pixels, one, then other. Okay. And if one goes summarised equal to summarised. Out of that image dot me and fire the okay. Okay, let's see now. We're converting it to a normal image array. Let's see if it will be doing it. Okay, great. We got it. Nice. Now we'll be converting this into a quick visualization. Always before pre-processing, we should know that we should verify how the image looks like. Is it correct or not? Okay. That's now add the text. So visual thing, I'll directly write the code. Oh, sorry. P RGB CLAHE to AI. Raster, if you are opening and you are watching it, you are great. Write something good on the comment section. I'll definitely check. Okay. Oh, great. We got the imagery, first imagery, how it looks, and the proper footprints as well. Great. Okay, let's now see like how we can extract this uh, footprints. But before that, we need to be pre-processing the image, like the grayscale, denoise, gamma, all these things we'll be doing it. So stay tuned. We'll be working on the next. So till now, what we have done is, if I'll see, we have installed a Rasterio, GeoPandas, CLAHE, PyPros, Matplotlib, and OpenCV Python, then PyStack client for taking the NF IP images, then import it. Then we have defined a bounding box of it. So the UI which we have taken is Berkeley, but Arizona. Then we have changed it in the CRS, like it was on degrees. Then we changed it to latitude, longitude, that is meters, basically. Then connect to the stack endpoint. From there we get the images that belong or that intersects with our AOI, and then after that we created a cloud optimized geotape, and then after creating that, then we see, like, we open the raster and we click with the AOI bounds, then we get our RGB set, or you can say the pixels files, and then after that we add it to a visualization, and we can see that now how is it looking. Okay, and now we'll be doing the pre-processing of this image. Okay, so now for the pre-processing part, so what we'll be doing will be grayscale, denoise, contrast, building, and the gamma. So basically, this is the secret, you can say, secret sauce of this project or this segment. This is where most people fail, and because you run edge detection directly on a raw image, it will be noisy. Okay, so we do four things. First will be the grayscale, because edges work better on one channel. Okay, blur, reduce the noise, so we detect garbage edges. We don't detect those garbage edges. Uh, the CLAHE, that is contrast limited adaptive histogram equalization, that is the full form of it. So that's why we are calling it CLAHE. That is for to boost the contrast of the rooftops. Okay, and then the gamma, that will be brighten the shadows a bit, so the darker roofs don't disappear. Okay, so basically pre-processing is the difference between random noise and usable frequency which we'll be having. So I have already written the code. So if you see, the first thing will be gray. I will be using the OpenCV Python library to which we have the image which we have already built into grayscale thing. So here it will be providing that. So it is basically I have written convert RGB to grayscale for edge detection. One channel image simplifies the edge finding. Then we'll be denoising it, blurring it. So denoise with Gaussian blur fast to reduce speckle noise. It will give cleaner edges with fewer false detections. Okay, that's where also we are using the OpenCV. Then CLAHE, that is contrast limited adaptive histogram equalization, where increases the local contrast and helps the boundaries. The result will be the the first one, which is it is like why we are doing it and what is the result of it of that particular code. Okay, so result will be roof edges becoming more distinct even under uneven lighting. So this is what the code is. So I'm not now currently writing the code and explaining because it will become a large uh, uh, more extended video, you can say. So that's why I'm now coming into like how we'll be doing this particular part. I'll be explaining this thing, but yeah, I'll be putting this thing. Then optional will be the gamma correction, so that we brighten the shadows a bit. Shadow groups are less likely to disappear. So we have taken the gamma value is 1.2, and then we have put it. Then the pre-processing, after this pre-processing stages, this four pre-processing stages, one is clear, grayscale, blur, contrast, and then this gamma. We plot this thing on. So this is where we have put it. Pipelines. It will be helping us to. So that's I have put a name. Put it. So this is actually my notes when I have created this project. So that's how we have created it. Okay, let's run it and see. How it will be shown. Okay, grayscale looks like this, blur and contrast looks like this, gamma adjusted will be looking like this. So all the four things has been done, and we got a final image of after that. That is after gamma adjusted, we have this particular image. Okay, great. Okay, now we run Canny edge detection. Canny looks for places where pixel value change sharply. So that's a boundary. Okay. Uh, Now the thresholds are like low threshold gives more edges, but more noise. Okay. High threshold gives fewer edges but miss the buildings. So we'll start with 50 by 150, and later you can tune that thing. It depends on how you will be getting the image, so you can tune that thing later. And the optional multi-scale why we are putting is like one blur size catches sharp edges, another catches soft edges. We can combine them afterwards, like so. uh, this Canny detection, it controls the sensitivity of the image, you can say. It is like adjusting your vision. Like you have a you can say that you have a spectacle, right? And you have a power, and then you have seen like when you do the power checkup, they add something so that the vision should be clear. So similarly we are doing something over here, and we are tuning that. So basically in AI models these are already tuned, and based on the image only it gets tuned, and that particular pre-processing edge detection can be done. So mostly those are already done. So now you are learning the basics, like okay, how this can be tuned in this thing. And this is the code which I have already written, and let's see the running, like how we'll get it. Okay, okay, can 5 by 5, 9 by 9, combine the edges. Okay, this is what the final look for the combined edges. Canny look, Canny edge detection. Okay, fine, got it. Okay, now we'll be going to the post processing. Pre processing part is done. Then after that we will post process the image. So now we'll be cleaning the cleaning it morphological. Cleaning will be done. So basically edges are lines, okay, and buildings should become the shapes. This is why the morphological morphology helps closing close gaps in edges. uh, that is one thing. Dilation thickens the edges. Opening removes the small noise specks. Okay, so morphology is basically cleaning the map after edge detection, we can say. So that's what we are doing over here. Let's run it. So if you'll see, like, morphological closing connects the broken edges, then the result will be like the roof boundaries become more continuous. Then slight dilation will be thickening the thickens the edges. That will helps to fill the shapes latter. Okay, more solid, you can say, more solid candidate regions means you can say that the proper bounding extractions will be exact, and then removing the small speckles that will be with the opening, so it will mark the cleaner building candidate that we have. So this one closed, dilated, and open cleaned. Okay. So now you can see that this this boxes has been appeared in this here. Okay, great, good. Okay, so let's now plot this thing and see how it has been plotted it out. Okay. Let's just see this thing here. It would be 7 by 7. Let's say 7 by 7, or what's it? 10 by 10. Okay, let's say 10 by 10 and see. Remove this, this, this. Let's see. Let's see the open clean one. Okay, so this is what it's now looking like. Okay, and we can also check this one as well. Okay, let's see that as well. Correct. Here I think left to right. The dilated one. Let's see means how the three images are looking, right? We can visualize that. Okay, this is somewhat like this. I can't find much difference in this, but yeah, there must be the post processing, like how they are doing it. So let's figure out the other one as well. Okay, so that we can see, right, how it has been done. The other one is the closed one, right? Closed. Hmm. The closed one, let's see that as well. Oh, okay, now you can see, right, how much how the image has got cleaned. Okay, here you can see that these are the steps, right? These are the snappy edges, and this has got clean. If you see the difference from here, here's the difference. Okay, like how it is like everywhere some particle bits has been over there, right? In the RGB scale, not in the RGB, in the grayscale. So here also you say it is slightly clean, and now here it is. We can see that how it has been added, the open cleaned one has been added. Okay, so that's the difference which we can plot it out in the uh, in our code, and we can check that out, correct? And now we'll be doing the connected components filtering. So now we have the blobs, okay, but there is still the noise is there. So connected component finds separate blobs, and then we filter it by size. Then small specks or the noise will be disappearing, and bigger steps will be, they will be remained over there. Okay, and this is a simple but powerful trick. Like you can basically tell the algorithm only keep the things big enough to be a building. You can say like that. So let's run the component filtering as well. Connected component filtering part. Okay, then the code. Okay, let me check. Yeah, so as I have written this code now, so connected component find the blocks groups of connected pixels. You can see what will be the result. Result will be we can remove the blobs, yeah, that are too small to be a building. So we'll level them, and then after that we'll be removing them. Then we'll create a empty a mask type of thing for filtering those components, and then after that based on the size threshold, base tuned on the NAIP resolution or the AOA that we have taken, it will be removing those tiny blobs, you can say. And after that we'll be plotting those things which can be a building, okay, based on the image resolution as well, which can be a building, that now we are checking it out. Okay, let's see. Okay, okay, it has filtered out a lot of things, I guess. You can see, right? It has filtered it out. That's 10 by 2, 10 by 10, because we are working by 10 by 10 plot size. Okay, whatever. Okay, extra one. Okay. Whatever. Okay, let's see that now. Okay, it has kept most of the things. Okay. Okay. Now, what we'll be doing is we'll be vectorization. Okay, that is called as vectorization process. Raster to polygons, clean up, and then we'll be simplifying it. Okay. Okay. Start this thing. So now the vector for the vectorization thing, what we'll be doing will be we'll be converting these raster blobs into the polygons. Okay, then we'll clean up that part, and then we'll be simplifying, and we'll be exporting it into a JSON file. Okay, so here you will see convert binary parts to polygons using Rasterio features. Start set geo data frame of candidate footprint of polygons in raster CRS. So here then remove the tiny polygons by area in meters, reproject it to metric CRS, then simplify the polygons to reduce the edges which are mostly jagged. Okay, so that we see the cleaner footprint shapes. And then back to WGS 1984, that is WGS 84 for web mapping and for visualization. We'll be changing it. Then uh, we'll be putting it into our GIS file. Okay. So let's remove this part for now. Okay, and run this. Okay, we got the thing. Then export your so okay, we have not import this. This also what we have not imported that. Okay, we have imported the OS and we have ran it. Okay. Now what we'll be doing is we'll compare this with OSM, OpenStreet model, OpenStreet data, and we'll see like how it is looking like. Okay, now we'll be comparing with OSM because we are not publishing this as an official footprints. This is a baseline, okay. But we can do is a quick validation. So OSM buildings are community mapped. Okay, so we fetch the building polygons in the AI which we have already, and then we'll be validating. So OSM is also not perfect everywhere, but it's a great reference layer for our project, so that we can see that okay, whatever work we have did is correct or how close we are, so we can have that. Okay, so basically we have fetched this. I have written y and the result. Okay, and let's see that. Then after that we'll be computing it in IOU style overlap. Okay, so basically we got the length of OSM buildings, that is 1173. Okay, so compute, so simple overlap matrix IOU like union based. So IOU means here, now let's explain what is IOU in simple words. IOU means overlap divided by total combined area. Okay, if your IOU is closer to 1, it matches well. Okay, and if it is closer to 0, it is 4. So this is the perfect science. This is not the perfect science, but yeah, it gives us a quick to test like okay how close we are. So let's see what will be our IOU. Okay, it is coming to overlap pact will be uh, not closer to 1. It's much farther than thing. Okay, let's see. The 7 metrics will be this one. To some buildings. So the candidate polygon that we got is 31. OSM buildings that we have is okay 1173. That is not a good result. Okay, so but yeah, we have received some particular polygons inside that, so we can find that okay this is the matrix which we got, and we can fine tune more perfectly into that and make the result will what we'll get will be good. Okay, now let's go to the what I'll say uh, maps and interactive visuals, how it will look like, and we can see over there. and we'll be finding out what is the final insights what we got from this project. Okay. Okay. Okay, now we'll be writing the interactive visuals and we'll show you how it has been done. After our IOU score, I also tell you the what is the analysis, final analysis of what we got from it, and I'll so that the so the it will be understandable like what we have done, how we can compare it, how the things can be done. So all those things can be now we can provide it. Now let's to make it presentable, we will be creating a 2 by 2 panel, and it will be like figuring out the plots what we have, the images or the plot graphs that we have created, we will plot it out. Okay, so for that, when you see that original NAIP that we got, then we pre-processed it with contrast and gamma. This is it. Then the edges or the canny that we have provided. Then the candidate blobs, fruited blobs. Okay, so this is it. And then now after that, what we do is we overlay those footprint candidates into the and OSM buildings interactively, so that we can see it out. So we built it in this folium through folium we have created it. So if you see now, so we have achieved a good result over here. Like if you see, like, right, so most of the footprints, building footprints has been made out. Okay, like this you will see is the rectangles one and this snappy edges as well, we got it. So you will see over here as well, we got the footprints. Okay, so now let's discuss about what is the main analysis. Okay, interpretation and the limitations that we have. So I'll be adding it as a whole descriptive thing as a theory or can descriptive thing on this particular notebook part, and you can go through that as well, and we'll also check how the analysis has been done. So let me write the analysis and then I'll be showing it to you guys, or we'll be discussing it out, and what next can be done on this thing, that also we'll be discussing it out. So I have written all the analysis and interpretation, the limitations that we have over here. Whatever we have done, I have also added how the particular industry analysis, why it matters, what's the stats mean. That is also the limitations, key limitations that we have. I have added it. Okay, so let's go through that. Let's read it out what I have added. So the analysis and interpretation and the limitations are of building footprint extraction using edge detection. So the overview of evaluation results is the extracted building footprint candidates were evaluated against OpenStreetMap OSM building footprints, which serve as a widely used community curated reference dataset. So summary stats that I'll add the picture over here. So let me add it as well. Okay, so yeah, I have already added it. So in the summary statistics, if you see that candidate polygons extracted is 31, OSM building footprints is 1173, intersection area is around 874.32 meter square, union area is this one, intersection over IOU over union will be like 0.00257, which is the overlap with our OSM balance is 0.26%, which is less. I got to know means it is less. So the interpretation of IOU score. So what IOU represents is intersection over union is defined as area of overlap between the predicted and the reference buildings divided by the total combined area of both. So it answers a simple questions like how much we predicted actually that matches with the known building footprints. Okay, so as the IOU score which we get is 0.0026 means uh, only a very small portion of building area that we have identified by has is overlapped with the candidates that is there already there in the OpenStreetMap. Okay, the extracted building footprints represent a small subset of the total built up area within the AOI. The result is expected for a pure age based non AI baseline method and should not be interpreted as failure of the workflows. So, what is the relationship between the visual results and the metrics? So, visual observation, what we found, like over here, if we see like this one, right? Uh, in the visual representation, which we looks like it is that the AOI contains a dense suburban residential layout with hundreds of individual building footprints. OpenStreetMap shows a high building coverage and completeness in the region. The extracted candidates building footprint candidates are fewer in number, that is 31 to a large well-defined rooftop structures with clear continuous edges, building with minimal shadow and vegetation interference. While this matrix is so low, the IOU is heavily influenced by the scale of imbalance. Okay, so OSM building structures showing that 1173 polygons, a large area, but the extracting candidates 31 polygons, very small intersection area because IOU is computed using dissolved union geometries, even visually reasonable candidates like footprint candidates contribute very little to the total overlap. Okay, so why this result is technically correct, not a failure. Okay, so this project intentionally uses a classical computer vision baseline rather than a trained segmentation model. Okay, so the important context over here is Canny age detection identify the boundaries, not filled objects, and building must be reconstructed indirectly using morphological closing, dilation, or let's say connected component grouping. Okay, and any break of edges, trees, shadows, roof color variation prevents formation of building spaces. Therefore, the algorithm is structurally based towards under detection, prioritizing the precision over recall. Okay, this makes it suitable as a baseline can let's say building footprint generator pre-processing steps for the AI models, and let's say like this is not required. Okay, so the key technical limitations that we what project we have created is the edge detection baseline limitations, that is roads, parking lots, pavements, and also has strong edges, right? Trees and vegetation disrupts this roof boundaries. Roofs are similar color to the surroundings are poorly detected. So basically, now it will ask me. So okay, let me tell you. So that results like many true buildings never form closed edge loops. Okay, and morphological reconstruction constraints will be morphology assumes edges can be closed into shapes in dense residential layouts. Roof adjacency creates ambiguity. Let's say the aggressive filtering effects, pixel area filtering. If you see like pixel area filtering, polygon area filtering. So basically, this removes small residential buildings, narrow, complex roof structures, which results in like the candidate or this particular building footprint candidates count is drastically reduced and lowering the recall. Okay, then there is this evaluation method bias as well. That's also a different part, like global IOU using dissolved geometry penalizes the sparse predictions. Okay, a few good prediction cannot compensate of thousands of missed buildings. So IU does not distinguish between fewer high quality detection or many low quality detections as well. So better alternatives for the future world will be tile based IOU, per building matching, and precision recall or sample buildings. Okay, which are already there. So what this analysis tells us, it is fast and lightweight. Okay, no training data is required. Fully explainable and reproducible. Ideal for rapid mapping, exploratory analysis, educational demonstration, and candidate. That is, candidate means the building footprint generation pipelines. Okay, weakness of this approach will be like low recall in dense residential areas, highly sensitive to shadows and vegetation, not suitable for the production grade building extraction as its own. So, and so industry analysis why this matters is a big idea will be like building our assets on the ground. Many industries need fast way to estimate where buildings are, even if the result is not perfect. So, edge detection is the simplest computer vision baseline. It does not understand buildings like AI segmentation does, but it gives you quick footprint candidates you can refine later. Okay, where it helps immediately is fast mapping that I have already told you, operation planning's risk that we can do. What evaluation stats means like intersection areas, how much of our predicted footprints overlap the OSM buildings, that is the IOU which I was talking about. Union area, like the total combined area covered by the either prediction or OSM that we have already showed in the matrix. Okay, uh, and the other things. Orange limitations will be like that is uh, road and parking slots also have edges, false positives. Okay, these are the false positives which can be limitation of this thing. Trees and shadow breaks roof edges, that is mesh buildings, work best when imagery is high resolution. Okay, correct. So the perfect upgrade path after this will be, this we have set the baseline. Okay, now the baseline of how the building footprint extraction, that the age can adjust, that can be done, that we got to know. Right now we can compare this thing against with the same data set. We can compare it with unit segmentation, SAM based extractions, and there are some SRE pretend building footprint models are there. So it has, I think, what I know is like there are for the different regions of countries, so they have different types of building footprint detection which they have already pre-trained. So using that as well, you can pre-train and you can check the score with, I can say that IOU and with OSM state maps, OSM, yeah, and we can check that thing. So the final conclusion of this project, what we got is the low IOU score is a correct and meaningful outcome. Okay, reflecting the inheritance of these limitations of age-based buildings, building extraction in a complex urban environment. The project successfully demonstrates like how building footprint candidates can be generated from an imagery. Okay, how classical computer vision integrates into the GIS workflows, how spatial accuracy metrics should be interpreted critically. Most importantly, it establishes a solid foundation from our advanced methods such as deep learning based building segmentation and multi-temporal change detections and everything. So this is the final conclusion of this project, and I believe try this at your system and find it out. You'll get to know about the process of how the building extraction can be done with the simple computer vision baseline models. Then you can go with unit segmentation models, SAM based extraction like SAM 2, I think already there. Then yes, repeated models are also there. You can work on those things. So the outlining of this is what we got. I have put all the conclusion, analysis, and the limitations in this particular file. So you can work on this thing, and then after that you can get to know like how this has been figured it out, and after that you can work on your own models, and you can create them and you can work on them. Like this is the basic understanding baseline of the project what we have done. So I hope it helps you in understanding this particular process. So by this Python project, you could able to now do the building extraction. You can do the correction, preprocessing of the image with the grayscale, and getting the denoise out of this project, out of this images, and then after that you can post processing it, and by simple Canny edges removal of those and morphological correction, and then after that you can plot it and you can see it in the map. So this is the whole pipeline of this particular project and which you can do, and the architecture is simple. I'll be adding all these things in the GitHub, and you can, and please comment footprint on the comment section, so that I'll be adding that to the comment section, the GitHub repository, and you can look into that. Already we have covered one population density Python project, uh, which is already published in the YouTube. I'll put that in the description of this particular video. You can go and you can check that out as well. And stay tuned to Native GIS, so that you will be getting more updated videos related to GeoAI, GIS, Python based projects, workflows, utility based projects, and everything on this. And stay tuned to our LinkedIn page also, because now we are going to start a series of explaining how the DLPK package of S3 has been created and what is the meaning of all workflows. Thanks for watching. If you found this video helpful, give it a thumbs up, subscribe to the channel, and hit the bell icon to stay updated on the latest in AI and GIS. See you in the next video.